Hello YouTube, this is Dazza the cameraman. Today is Thursday, February 21, 2019, that's New Zealand time. I'm very pleased to have with me as a guest, All Grey Matters. Hello All Grey Matters, how are you today?
Hello Dazza, I'm great today in a nice sunny but snowy day in Kansas.
Right, and what is the time there for you at the moment?
Right now it's 6:38 in the evening.
Right, so you're still on Wednesday.
Affirmative, yes.
Right. Okay, now we hope to have Astronomy Live joining us soon. Unfortunately, he has had something unexpected come up, and so hopefully he can join us very soon and present the results of his live stream that he started, that he streamed last night, filming the moon side by side with an alt-az mount and a polar-aligned equatorial mount. But in the meantime, All Grey Matters and I are going to discuss Mr. Thrive and Survive and his recent videos and claims. Now, as you can see, I've got All Grey Matters channel shared here. And if you haven't already, I'd encourage you to go over to All Grey Matters channel and subscribe. He's got some excellent videos here dealing with moon field rotation and other aspects of flat Earth claims. So I know he would appreciate your support. And we're going to also take a look at one of his very latest videos, which I've already shared on my channel. But if you haven't seen it already, we'll take a look at that and will give us a basis for starting to discuss what we're seeing in Mr. Thrive and Survive's videos. So, All Grey Matters, if you'd like to give us a bit of a commentary as we're going through your video here.
Okay.
So I see you using Stellarium here, and you're actually downloading it onto the computer you're using at the moment. So hopefully we can pull that up. I've also got Starry Night going. But use Stellarium here to demonstrate what we see with field rotation. Would you like to describe some of the mistakes that Mr. Thrive and Survive is making in his videos?
Well, one of the things that I found was on his channel, where he was describing his video regarding the observations that he took, is that there was an assumption that regarding the rotations of the moon that we observe. And the point of this video was to point out that there's multiple sources of those rotations. One of the rotations that we should see is the field rotation, which has been discussed, and I think that Mr. Thrive and Survive does understand. And when you cancel that out with an equatorial mount, we remove that from the equation. And that's what I'm describing here so far, I believe.
Right. And then in your video, you move on to discuss some of the other rotation that we should expect to see.
Well, I think that the next thing that needs to be understood by those that are using this as evidence for a flat Earth, or against a globe anyway, or for whatever the evidence is supposed to be produced, whatever they're trying to claim here, is that they're saying, okay, we're using an equatorial mount, now we should not see any rotation. But that's not true, because the moon orbits at it has an orbit that's not coincidental with our equatorial rotation of the Earth. So as you can see in this video, the line that's going through the moon is representative of the orbit of the moon. And you can see that it's changing, and as it changes, the moon rotates also.
Right.
In this case, it's rotating in a counterclockwise direction.
Right, and this is because of the tilt of the orbital plane with regard to the Earth, correct?
That's correct. And you can see that, and this is simulating an equatorial mount. And Stellarium and the other software that, for instance, the one you're using, they do a great job of representing what we do see in reality.
Right. Now, I'll just pull that back here to what we're about to see start happening. And you might like to describe what we're seeing in this next bit, because this is the third motion that you talk about right here.
This is an interesting motion, and it's caused by the rotation of the Earth and your position on Earth. And if you look in my other videos, I was having some trouble determining what it was as at least the way Stellarium was describing it. And I found actually a bug in the Stellarium software that if this rotation or this observation that you're seeing here, where it kind of pulses and it gets bigger and smaller, should not appear at the poles. So if you set your viewing location to the north or south pole, we should not be observing this. And when you do that in Stellarium, it actually doesn't go away. In fact, it gets as strong as it was at the equator. But just today on my channel, someone pointed out that if you move your viewing position to the north, that effect gets smaller and smaller, which is what we would expect on due to why that effect is happening. So it gets smaller and smaller until you get exactly to the North Pole, and then it gets really big again, like you're on the equator. So this is actually a bug that we found in Stellarium. And when I went to the Stellarium website, once I knew what the cause was, I actually found that it was a reported bug that they're working on.
Right. Now, this motion that we're seeing, this backwards and forwards sort of rocking motion, that is libration. And so go ahead.
Yeah, that's correct. So it's called libration, and it occurs on a monthly period, or at least the orbital period of the moon, 27.5 days, right? Right.
Now, of course, with this most recent full moon, which was on February 19th, that was a supermoon. In other words, the moon was at its closest point or perigee from the Earth, as well as being a full moon. So this is why the moon looked particularly larger, about I think it's 14% larger from an apogee moon, or when the moon is further away, and about 30% brighter. So, of course, with the moon being on an elliptical orbit around the Earth, it's not a perfectly circular orbit. Sometimes the moon is further away and sometimes it's closer. But is this motion actually due to the rotation of the Earth more than the distance of the moon?
Yeah, if you watch the video or if you simulate it in your software, you'll find that it happens on a daily period. So the elliptical nature of the moon's orbit does not occur on a daily period. So that occurs on a monthly period.
Yeah. So it takes almost a month for the moon to orbit the Earth once. In fact, that's where we get the word month from. It means moonth, because it takes approximately 1 month for the moon to orbit the Earth once. But this rocking motion is due to the rotation of the Earth. And as you explained in your video, of course, the distance is slightly closer when the moon is directly overhead than when the moon is rising or setting on the horizon, because of the distance, I guess, in the radius of the Earth. You've got that slight distance difference.
Right. Well, if you can imagine standing on the equator looking at the moon, and then you do a rotation, say you're at the point on the equator that's furthest from the moon, and you could somehow observe through the Earth looking at the moon, and then at the point when you're the closest to the moon 12 hours later, that's what this effect is.
Right. Now, did you see Mr. Thrive and Survive's latest video where he presented one of the 3 views of the moon, where it was jumping all over the screen like a ping pong ball?
Yeah, and the only thing I can attribute that to is just his setup.
Right.
I mean, we don't have any information of whether he's purposefully withholding that information, or if he says he's just setting us up for failure. I think that is just bad data, but he says he has more coming. So I'm curious to see, before I jump to conclusions, what that further data will be.
Right. Now, I believe that Astronomy Live may have some more information about that. I know he was discussing some points that Mr. Thrive and Survive had made, either in comments or in his videos. So it'll be interesting to hear that when Astronomy Live is able to present his analysis. As I mentioned earlier, Astronomy Live had 2 telescopes set up. One was on an alt-az, or altitude azimuth mount, which moves left, right, up, down only. and the other one was on a polar-aligned equatorial mount, which cancels out the field rotation. So he did a side-by-side comparison and will be presenting the results of his analysis on that. Unfortunately, he has been delayed. Now, do you have any other comments that you would like to make, All Grey Matters, about Mr. Thrive and Survive's analysis, what he's been presenting and so forth?
I think most of it's been covered. The reason I made my video was the missing piece was that I'm projecting that he's going to take issue with the counterclockwise rotation that he saw even on the equatorial mount. And I don't deny that that's something that should be occurring. And it's just something that's getting missed in the comment section. Do you understand what I'm talking about? It's at the end of my video.
I would have to review the video, but I suspect what you're talking about is the fact that the moon, the main rotation that we see, the field rotation, is clockwise, but at the start it rotates anti-clockwise before it tilts over and starts rotating clockwise. Is that what you're referring to?
Yes.
Right.
So I think that there's a couple things going on with that. One of the we should not be getting the clockwise rotation because of the equatorial mount, but we should be getting the counterclockwise, and it's just starting right at his observation time. Right. It's just, and that's due to the libration.
Yeah. Oh, well, there's actually another factor at play there. I've covered this in one of my response videos, and that is the fact that the moon is actually crossing more than 180 degrees of the sky. So just like we're seeing with the moon transiting the meridian when the moon is at its highest point, we've also got the moon is transiting the east-west line, and you can actually pick out the points where that counterclockwise rotation slows down and stops and then starts changing over to a clockwise rotation. The midpoint there, you can pretty much pick out the time where it slows down, and then when you compare that to when the moon is actually crossing the east-west line, you can see that that is actually exactly the same time. So what I'll do here is I'll zoom up, and just before I do, I'll just mention I see Sean Hufford is in the chat. Hi there, Sean. I wonder, Sean, if you would like to join us in the Hangout at all. Just let me know in the chat, and I can send you an invite if you like via private message. Just let me know. I'll just come back to that in a moment. So I'm going to zoom up on the moon. Now this is set to Alt-Az mode, not equatorial. And I'll run this forward, and we're going to see the moon rotating. Now, I can't remember if this was for the full moon. I might just take this back to the 16th, because I know that that was the date that I confirmed that on. Mr. Thrive and Survive had asked me to check that date. So let's go with that same date. And I think the moonrise was about 3:30, if I remember correctly. And so what I'm going to do is I will turn off the daylight so that we can see the moon clearly. And let's run this forward. Okay, so I've got time increments of 1 minute. I've got my location set to Phoenix, Arizona, United States, February 16th, 2019, 3:27 p.m. It's not on daylight saving time. And let's run this forward now. And you can see that the moon is actually rotating counterclockwise, and then it'll slow down. And it's actually already started now rotating clockwise. So as I recall, I think I picked out the time at around about 6:30ish. I'll just bring that back again and have another look. So it's rotating counterclockwise, slowing down. So yeah, we've got 6:47 now. I think I had it at 6:39. So we'll let this carry on. And there we see the clockwise rotation, which is normal field rotation. And then we transit the meridian at, what time is that? 10:23, so we've already passed the meridian and that rotation. And now we've got it coming back again, which would seem odd. You would think, now why is that happening? Okay, now the moon is below the horizon. I've just pulled it back. So what I'm going to do now is I'll zoom right out, And I'm going to bring this back to where we started. I'll bring it back just above the horizon. Now this time I'm going to zoom right out so that we've got an all sky view. And I need to have north at the bottom, because this is now a sky map. So we have to imagine that we are holding this map above our head, because normally when we look at a road map, of course, we're looking down on it. And so we've got west on the left, east on the right there, north at the bottom, okay? And what I'm going to do now is turn on the local path for the moon, and I'm going to step this forward in increments of 1 hour so we don't lose the path. And you can see the path that the moon is taking across the sky. And so we can see that the moon rose in the east-northeast. It crossed over to the southern half of the sky, and then it set in the west-northwest. But at this point here, it actually crossed over the east-west line, and this is when the rotation actually changes. So here, we've got counterclockwise rotation. It slows down. Then we have quite pronounced clockwise rotation. Then it slows down. And then we have the slower counterclockwise rotation in this part here again. So I hope that explains that. Now, all grey matters, I'm aware that you need to get away soon. How are you going for time?
I'm doing fine so far. I think I have about another 20 minutes or so.
Right. Okay. Now, was there anything, I know you were downloading Stellarium. Did you want to share anything with that? How was that going?
I think it's downloaded, but I'll just leave it set for next time unless something comes up.
Sure. Okay. So what I've just presented here with the moon crossing the east-west line, and I think probably what I need to do is put together a video where I actually do a side-by-side comparison of this all-sky view along with the tracking view, and compare the time that rotation changes over. I think that would probably be the best way to do it. But hopefully that addresses why we're seeing that reversal in the rotation there.
Well, these are all field rotation. Is that correct?
Sorry, what was that?
The effects that you're describing here are all due to field rotation. Is that right?
Yes, that's correct. Yes. Now, I see I've been asked in the chat, what software am I using? This is Starry Night Pro version 6. The latest version of Starry Night Pro or Starry Night is version 7. I prefer to use version 6 as I believe that the interface is a lot easier to use.
So I saw a question in the chat a little bit earlier by Sue Lynch. Why wouldn't the moon pulsate at the poles? And that's because the pulsing effect that we see is due to your position on Earth changing closer and further from the moon, depending on what point you are in the rotation. If you're at the poles, if you can actually see the moon, which is probably unlikely, but if you could see the moon through the poles, you'd find that you're not changing that distance is not changing, since you're not rotating anything other than just a rotation on the poles. Does that make sense?
Yes, and that also explains too why, as you mentioned earlier, as you get closer to the poles, that motion reduces, and it should reduce down to 0, as you say. But there was a bug in the Stellarium software.
Right, and that's being addressed by the crew that works on that.
Yeah, I guess there's not too many people who would be right on the North or South Pole. So, yeah,
or even close to it.
Hello, we've got Astronomy Live. Welcome in. Good to have you join us.
Yeah, sorry. Didn't want to interrupt there, but just want to let you know that I am here.
Okay, well, good to have you. And we've got All Grey Matters also in the Hangout. So just introducing you two there.
Good to meet you.
Nice to meet you, sir.
Now, Astronomy Live, I believe that you have got an analysis that you would like to present. Shall I share your screen? Are you ready to present that?
Yeah, give me a few minutes. Sorry, I'm not quite ready for that just yet. I'm still getting things configured here.
Right. Okay. Now it's going to be interesting, as I mentioned, a side-by-side comparison of viewing the moon over how many hours was it? About 4 hours, I believe, Astronomy Live.
Right. Yeah, it was 4 hours. Total webcast time was about 4.5, and I think I spent probably about half an hour setting up the polar alignment. And then the last few minutes as well, confirming the polar alignment with some photography.
Right. Now, we were discussing earlier some points about that Mr. Thrive and Survive regarding his setup or the polar alignment. I believe that you may have some more information about his setup and the errors that he was making.
Yeah, well, just that it seemed to me that I don't even know 100% sure that he was really polar aligned to begin with. The way he talks about things, about the polar alignment, at the very least, suggests some pretty rookie mistakes. For example, he keeps talking about it as if they were aligning directly on Polaris,
During the
aligning
day.
the axis. Yeah, well, even before that, they were aligning. He admits they were aligning based on his theodolite app. So they were, as I thought, guesstimating based on during the day where they thought north was going to be. And it sounds like they were pretty satisfied with the results when it got dark and they could see Polaris because they said it was right on Polaris. Well, Polaris is not right on the north celestial pole. It's about 2/3 of a degree off. So right off of the bat, even if you take them at face value, even if they did manage to somehow miraculously point it directly at Polaris during the day without being able to see it just based on their phone app, which it, by the way, seems unlikely that they could do that to within more than a couple degrees at best. But even if they had, they would still be off by 2/3 of a degree. And in reality, they're probably off by significantly more than that. So no, that is not how you properly polar align a telescope. As I demonstrated during my webcast, I had a very good polar alignment, not based on the fact that the moon wasn't rotating most of the time. That was the other thing. The argument seemed to be that, well, when it wasn't near the meridian, it wasn't rotating, so therefore we were polar aligned. No, that's not how that works. That's not what that means. As you guys were probably talking about, I'm sorry I missed the beginning of the webcast here, but as you guys were probably already talking about, the fact that the rate of field rotation is not going to be constant. This is another point they try to make. They try to claim that we say that the field rotation rate should be constant from rising to setting. That's not true at all. In fact, there's a formula for the rate of field rotation that shows, let's see here, RSC Calgary field rotation. There was, I forget who it was, somebody I was arguing with about field rotation a while back, was kept pointing to the RASC Calgary website showing a formula for field rotation and complaining that my software wasn't right because it wasn't using this formula. Well, the formula was just the instantaneous rate of field rotation. It wasn't intended to calculate the actual angle of field rotation, just the rate of field rotation. But it shows very clearly that it's not a constant rate. So the formula is relatively simple. It's the angular rate of the rotation of the Earth in degrees per hour, which is about 15 degrees, times the cosine of the observer's latitude times a fraction of the cosine of the azimuth divided by the cosine of the altitude of the moon. And so with that, you can calculate the angular rate of field rotation. And so it's, as you can see just by looking at the formula, it's not going to be constant as the altitude and azimuth of the moon changes. So too will the angular rate of field rotation, even if the observer is staying in the same place. So no one ever claimed that it was supposed to be a constant rate. All right, so hang on a second. Let me rejoin on my PC here. I'm actually on my phone at the moment. Let me switch over to my PC real quick, and I'll rejoin in 2 seconds.
Okay, and I'll just fill in while you're doing that. So Astronomy Live mentioned about the actual position of Polaris, and again, this is indeed a rookie mistake that many of the flat earthers make, especially when they're talking about star rotation. Now, the yellow circle that you see there is actually the same angular diameter as the moon or the full moon, And let me just change the time here so that we've got the moon in view so that I can actually demonstrate that. So I'm going to zoom in on the moon. And you can see that that circle. Now remember that the moon is actually closer than normal at the moment, so that's why it is actually outside of the yellow circle. If we're talking about the average distance to the moon, then the moon would fit just inside that yellow circle. Sometimes it's further away, sometimes it's closer. So let's go back to Polaris, and I'm going to use that yellow circle to demonstrate actually how far away Polaris is from the North Celestial Pole, using the diameter of the moon as a guide. The other thing that I'll do is to turn on the celestial poles. So there is the North Celestial Pole there. And so we can see that Polaris is actually about 2/3 of 1 degree from the North Celestial Pole. Let's measure the angular distance to the North Celestial Pole. And we've got around about 40 arc minutes. Now there's 60 arc minutes to a degree. So 40 arc minutes of 60 is 2/3. In other words, you would actually fit the moon within the circle that Polaris scribes around the North Celestial Pole about 2.5 times. So if you imagine the size of the moon, that's actually quite a distance from the North Celestial Pole. So, you know, if you're doing a true polar alignment to the North Celestial Pole, if you're focusing just on Polaris, then it's not going to be truly aligned. Astronomy Live?
Hey, so I'm rejoined now, and I'm going to be resharing here my webcast from last night. I don't know if did you guys cover this at all?
We just touched on it, but really waiting for you to present. So your screen is now presented to everyone. Okay,
great. So yeah, basically,
just before you do carry on, I'll just check with All Grey Matters, because I know that he does need to get away soon. How are you going there?
I'm doing okay so far. I'll let you know when I need to take off.
Great.
I would like to point out, if I have a second here to do that Rich, Mr. Thrive and Survive, is claiming that his polar alignment is irrelevant because he has. I'm just saying what's going on and what he's claimed.
Yeah.
And it may be, if it's depending on what's the cause of the rotation. I'm projecting that he's going to use a number of things that are showing that counterclockwise rotation that might be irrelevant to the polar alignment of his equatorial mount.
Yeah, I mean, it depends. If he's got a really bad alignment on the equatorial mount, that's going to do some, you know, aberrant rotations that wouldn't necessarily, well, I guess you could call it it is field rotation, but it's field rotation due to bad alignment. But as you said, yeah, they may, I don't know if he's going to try to focus on more subtle aspects, like factors that don't have anything to do with our viewing perspective, external to the telescope and everything else. Factors like libration. So let me share, yeah, this shows it pretty well. Let me share a different window with you guys here. I know I'm sharing the video at the moment. So where's the Hangout window? Here we go. So let me share, hopefully GIMP will let me share a window here. All right, can you guys see this?
Yes, I can.
Okay, cool. So I took a screenshot here from the beginning and from the end of my webcast. And this is with the 8-inch LX200 that was polar aligned. So we confirmed during the webcast that the polar alignment was pretty darn accurate, pretty good. Let me try to line these up a little better. And then let's see. Actually, it needs to come down the other way. Oh, no, wait. I had it right the first time. This way, like that. Yeah, that's pretty good. So now you can see when I blink these two images that are about 4 hours apart, you can see some motion in the moon here, but this is due to libration. As you can see, the moon's not rotating like a clock. It's not rotating any really significant way. It's just that our perspective of the moon is changing, our angle of viewing the moon is changing as it's moving through its orbit around the Earth. And so this is due to libration. It's a combination of libration due to its orbital motion and diurnal, what we call diurnal libration, libration due to the rotation of the Earth, and me as an observer standing on the side of the Earth and here in Florida, having a different perspective of it being carried to a different distance from the moon, and this produces this apparent shift in it. In fact, if you blink them fast enough, you can start to get a sense of the moon's three-dimensional shape a little bit there. And if I were really clever and lined these up, I could probably even produce a stereograph of the moon using these two images. So yeah, you can also see very slightly, and if you look on the right where the craters are, you can see a change in the phase of the moon too. You can tell which one was further from the full moon, where the shadows in the craters are a little bit deeper and a little bit darker. So yeah, that is quite normal, and that is due to libration. It doesn't have anything to do with the field rotation. The polar alignment was pretty darn good. But if you compare images that were taken through the altitude azimuth scope, it's a whole different story. And this is really what most of these people seem to be, talking about and showing in a lot of their videos earlier, was this dramatic rotation of the moon from rising to setting. So if I go back earlier in the webcast, you can see that Mare Crisium's up at the top, Tycho's off at the right, Aristarchus is down at the bottom. And by the time the webcast was over, by the time I shut that scope off, it had basically rotated 90 degrees from where it had been. So, this is field rotation here on the left. This is due to the telescope being in an altitude azimuth perspective versus a polar aligned perspective. And as you can see in that previous blink test that I did just now, I did eliminate the effect of field rotation by polar aligning the telescope. And the other thing I did is to verify the polar alignment of the telescope. I pointed it at the north celestial pole at 90 degrees declination. You can see Polaris is right at the edge of the field of view. I'd actually zoomed out more than what you saw there on the moon earlier. When I came back to do that, I basically had to put the focal reducer at a further distance from the camera, so that the camera was at basically in a star diagonal. It would have a greater distance to the focal reducer, and that reduced the magnification. Bottom line, as you can see, the moon's much smaller in the view now in that configuration. So thanks to that, I am able to barely fit Polaris in the view at about 2/3 of a degree away from the north celestial pole, which is basically in the center of the image, although I'm zoomed in here, so you can't really tell, but the center is off on the left. So this image was taken by allowing the stars to rotate on their own a bit. Let's see, I'm trying to find the image that I took. So this is the image I took by manually rotating the telescope in the right ascension axis. Now, if I'm polar aligned accurately, the circles that are traced out by the stars, you can see how these stars are streaks. If you imagine a circle running through those streaks, they should be concentric, and they should be in alignment with star streaks that you produce naturally by just letting the telescope sit there without tracking the sky. So that's what I did here. So you can see the comparison there, and you can see that they're streaking the same direction. These stars up here are streaking this way, Polaris is streaking this way, and if you imagine circles running through these star streaks, they would be in alignment pretty closely with the stars that are streaked when I move the telescope manually here. So that tells you, that's proof right there, that the polar alignment was accurate, and that's why I was able to eliminate field rotation as well as I did during this 4-hour period of tracking the moon. And yet on the left here we have this altitude azimuth scope, and you can continue to see field rotation quite significantly. So I want to see the rest of his footage. I don't know if he's uploaded it yet, but he talked about having more footage that he hadn't shown yet, where you see this really sudden shift in the moon. Now, I can think of a number of reasons that can happen. One is the most obvious: you bump the camera in the telescope mount. The way these cameras are set up, generally speaking, there's nothing to prevent a telescope camera from being rotated in the eyepiece holder. You can orient it any direction you want, and if it's not on perfectly tight, even if it is somewhat tight, if you don't have 2 screws holding it in place, if it's one of these cheap star diagonals that does a 1-screw hold, then it's not necessarily going to remain fixed. It'll be very easy to rotate it in the view. And so I think that can happen. That may have happened. Let me see if I can share a photo here. Where's my... Okay, let me see if I can share this window. Okay, it's not going to let me do that with that program. All right, well, I'll just bring it into GIMP then. Where's... okay, I'm looking at the wrong window now. Let's see. Okay, that's not what I need. Let me try this again. Sorry. Hang on, bear with me 1 second here. I'm going to try to pull this photo into GIMP.
Yes, and just a response to Match Rocket, you're absolutely correct. The flat earthers will have to invent a new phenomena to account for moon rotation. Any bets on who will come up with it? And this is something that we see time and time again. Of course, we love to refer to the term flurspective. It seems that there's always some sort of magical explanation that has to be invented to explain away what we see. I call it trying to whack a square peg into a round hole.
Exactly. So in this photograph, you can see the two telescopes that I had set up. You can actually see the webcast going on there in the left on the laptop screen. And I've got the Samsung camera on the white telescope. That's a refractor. That's the Orion. That was set up in an altitude azimuth perspective. So you can see how that telescope tracks by moving left, right, up, and down. The base sits flat, parallel to the horizon. So that's a altitude azimuth alignment. And although it's hard to see there, this star diagonal that connects it, let's see if I can grab a little highlighter right here. So this star diagonal that connects the telescope to the camera and basically orients the camera 90 degrees away from the telescope was necessary for one thing, to prevent it from potentially colliding with the mount down here as it rose higher. But also, with a lot of these cheap star diagonals, including this one, there's only one screw holding that camera in place. You can take your hand and rotate that against that screw pretty easily. And so if you are clumsy and you fumble it, even if you don't mean to, you can bump the camera and potentially jerk it, 5 degrees, 10 degrees, not too difficult. And so I actually found later on in the webcast that even when I set it up, I thought it got it on there perfectly straight. It wasn't perfectly straight. It was about 5 degrees off. But it didn't matter because I was mainly interested in the total amount of field rotation, not the absolute orientation so much, but the change in the orientation over time. So it didn't really matter as long as I left it alone, which I did. I did not touch that camera because I didn't want to accidentally bump it and introduce a change in the orientation that really wasn't there. So on the left, we have the blue tube. It's a very dark tube. It's hard to see, but the LX200 telescope. And what you're actually looking at there is the bottom of the telescope, and you can see how well used this telescope is. I've had it for, 15 years now. And you can see all the scratches on the bottom of the tube there, or on the bottom of the telescope there. That's where you would normally connect it if it were altitude azimuth aligned. Like the telescope you see on the right, it would have a connection with a shaft going through the bottom and straight up into the telescope. And so normally when you put this thing down on its tripod, you kind of have to hunt for it a little bit and until you get it in the hole. And so it tends to scratch up the bottom of the telescope. So that's just normal wear and tear. But you see it here because it's actually sitting on a wedge. This whole section here, this is actually a wedge that's tilted it to be equal to my latitude, so that it's pointing out at the North Celestial Pole. So actually it's 90 degrees minus my latitude is the angle at which it's actually oriented, so that if you were on the equator, it would have to be tilted 90 degrees with the flat bottom of the telescope actually vertical. In this case, it's a little bit less than that because I'm in Florida, but it's still heavily tilted over. And so that's what happens when you polar align. That's how you polar align. It's actually oriented parallel to Earth's axis of rotation. If you imagine an axis that runs through the bottom of the telescope out through the fork arms here out to the top, that would be pointed right at the North Celestial Pole, not Polaris, the North Celestial Pole. And so that whole thing was aligned early in the webcast. And then once I got it set up there, I provided that view for comparison. So I had a Canon camera sitting on the back of the orange tube that was delivering video to the same laptop, so I was able to have side-by-side video. And so I kind of wonder, I want to see, like, first of all, I want to see a picture of his telescopes being set up so that we can get confirmation, first of all, that they really were equatorial telescopes. And second of all, I want to see what I just showed a minute ago, where you have star trails of Polaris with the drive shut off, and you have the same exact concentric circles produced when you physically move the telescope or use the motors to turn the telescope in the right ascension axis. If you've polar aligned things correctly, those should line up and be nice concentric circles. If not, they will have a different center of those circles. The circles will appear to be circling two different points. And so that's how you can easily prove that you actually do have a good polar alignment. And I question that. So there's a number of pitfalls there that remain to be investigated. But what is clear from my footage is that when you do have a telescope that's properly polar aligned, you don't get field rotation. You get a nice clean image where you don't see that kind of rotation. You get a nice consistent orientation of the moon. You do have libration, but you don't see that rotation aspect of the moon. So just to show the libration again real quick, because I think it's pretty cool in any case, is if you blink images here from the start and end of the webcast that I did.
Are you able to zoom that up at all, or?
Yeah, that's a good point. Let me zoom in here. Yeah, that's about as zoomed as I can get it without going too far. But yeah, right. Yeah, you can easily see there the change in orientation, a physical change in orientation of the moon due to diurnal libration as well as other components of libration. But as you can see, it's a much more gradual and subtle effect. Yeah. And you don't see that kind of rotation of the moon that you see with field rotation.
Mm. Now, I've got your video. You asked me to download it last night, so I've got it ready to go. And so what I thought I'd do is, first of all, I'll share my screen and we'll take a quick look again at the time lapse that Mr. Thrive and Survive presented. And then I'll scrub through your video and we'll compare the two.
All right. Oh, one other aspect I forgot to mention is that in mine, you will notice the moon drifting. But if you watch carefully, the polar aligned view really only drifts in the north to south direction. And there's a reason for that. It's because the telescope, all it's trying to do originally is track the stars. Now, I did set it to be tracking at the average lunar rate, but it's still only going to move in one axis because it's expecting to be polar aligned, which means it only needs to turn one axis to keep up with Earth's rotation. And so as a result of that, it will not turn in the declination axis, which is the north to south direction. And so you would expect that if you watch the moon over many minutes and hours of time, you actually do get a drift in north to south because the moon is actually moving in that direction. And I believe if you watch, you'll see the moon moving from north to south in my images very gradually. And that's because the declination of the moon was decreasing at the time. If you look back at Starry Night or any other program, or even my own spreadsheet, you'll see that the declination of the moon was gradually decreasing throughout my observing period. And so that is a natural consequence of the fact that the telescope's not trying to really actively track the moon. It's just tracking the rotation of the Earth, and it's trying to do it at the same rate that the moon is moving through the stars, but it's not trying to compensate for the declination motion of the moon.
Right. And there's something else too that I think should be pointed out. So here we've got the video from Mr. Thrive and Survive called "Here is the Moon Evidence That Doesn't Exist." I think I'd have to agree with him. I think he picked a perfect title for his video, ironically. And here is the video from Astronomy Live with the side-by-side comparison. And one glaring difference I notice is the field of view of the videos. So Astronomy Live is actually zoomed right in on the moon, and anybody that has operated a video camera with a good zoom on it knows that the more you move the camera, or the more zoomed in you are, any movements that you make of the camera are also magnified. So in this view, in Mr. Thrive and Survive's video, we're not really zoomed in very well on the moon. It's certainly not a very a tight fit, so any movement of the camera would be shown a lot less. But it's interesting what we see. So let's have a quick look. And how are you going there, All Grey Matters?
I'm doing fine so far. I'm going to have to leave in a few minutes, though.
Okay. Just feel free to jump in and talk over me if you need to go there. So I'm going to play a little clip. This is a time-lapse video from MrThriveAndSurvive's video. And as we can see from the start, that is playing. It should start moving in a moment. And so we've got the clouds there. And we can see already that the moon is bouncing all around in the sky, which is what caused us to question in the first place whether the mount was actually set up correctly. And this is an equatorial mount, by the way. It actually gets worse. He did mention that there was a battery change that needed to be done, but we're seeing an awful lot of movement. And then towards the end of the video, we see that the moon starts drifting consistently to the left and has to be corrected all the time. And I do wonder if maybe the batteries powering the tracking on the mount had actually gone flat and he had actually lost tracking. That's my suspicion of what's going on there.
See, that to me, it looks like he's bumped the mount. I mean, it could be an equatorial mount and he's bumped it. And so it's not even close to a line now, and it's really drifting bad. Right. All it takes is one good swift kick, especially if your mount's relatively cheap.
Yeah, here we go. So here is the movement to the left that I was talking about. So I suspect that he has lost his tracking altogether at that point. So as I've said many times, to me it looks like the moon jumping all around like a ping pong ball. By comparison, we're going to look, I'm going to scrub through Astronomy Live's video, and yes, there will be some movement as adjustments are made and so forth, but we see that the movement is considerably less, especially when you consider the degree to which Astronomy Live is actually zoomed in on the moon. As I say, the more you zoom in, the more any movement is magnified. Sometimes the scrubbing actually stops, so I have to play a little bit there.
Right, and it should also be pointed out that, on the left we have an altitude azimuth telescope, which is not going to be as accurate as a polar aligned telescope in the first place. Secondly, it's a $400 mount versus a $3,000 telescope. On the right is the polar aligned LX200, a much higher quality telescope. And like I said, you see there, the motion is almost entirely in the vertical axis, up and down, up and down. That's because that's the uncorrected component of the moon's motion in declination. Left to right, it is extremely solid because it was very accurately polar aligned. And so in the right ascension axis, I really don't have to make many corrections at all. It's pretty much dead on there. It's just the north to south direction that is uncorrected as the moon's declination actually does change over the course of the night, which causes that bouncing motion. But as you said, Daza, here I am. I've got way more magnification on the moon than he does. My moon barely fits in the field of view of the frame, and yet I'm not having to chase it all over the place like he is.
Exactly, and just for effect, I think I'll go back to his video again and just play it again so that we can see it bouncing all around the sky. I love seeing that. And also, I think it should be pointed out too that your telescopes are not set up permanently. If your telescope was set up on a permanent pier and very carefully aligned and so on, we wouldn't be seeing any drift, really, would we?
No. Well, and you'd still be seeing the north to south drift only because the telescope is not designed to track in declination while it's polar aligned, and the moon is moving in declination. So that's always going to be an uncorrected component. The only thing you could do there is you could use theoretically, you could actually use my NEO tracker software, load up the moon's orbital elements, and have it directly track the moon's orbit. That would eliminate the drift altogether. I didn't think to do that. That would have been kind of funny to try.
That sounds like a good next video.
yeah, that's a future goal, future directions right there. But with the altitude azimuth scope, it's just it's a much cheaper telescope. It's a simple next star mount, and it's altitude azimuth aligned. So it's trying to track with 2 motors instead of 1. So you basically double the amount of mount error in what is already a cheap mount with cheap gears by comparison. And so you're not going to expect that kind of tracking accuracy. But out of a polar aligned scope, even a cheap one, you should get superior tracking. And that's what you saw with with my LX200 video for sure.
Right.
And here we should be seeing, pretty consistent tracking. This really odd sudden shift where it's tracking reasonably okay, although it's bouncing around a little bit, but it's tracking in a reasonably consistent manner, and then suddenly starts drifting wildly off in one direction, is very symptomatic in my mind of either, like you said, the motor's dying because the battery's going out, or he's kicked the mount, or maybe he's bumped it while changing the batteries, and it's now drifting because he's not even close to aligned. And so you really have to watch your alignment, especially when you are polar aligned. With an altitude azimuth mount, you can always quickly resync on a star or a planet, and because it's tracking with both motors, it's basically an alignment that is entirely digital. It's in the computer of the telescope. It says, okay, I know where I'm pointing right now in the sky. I know the layout of the sky, so I know how to track. When you're tracking with polar alignment, you are relying on a physical alignment of the telescope. The telescope needs to be physically parallel to the Earth's axis of rotation. So even if you resync the computer and tell the computer, hey, this star over here you're looking at right now, this is Sirius, it's not going to help your tracking at all, because it's relying only on one motor to do the tracking, and that motor has to be, the axis of that motor has to be aligned parallel to Earth's axis of rotation. So it's much more demanding in that sense.
All right. Okay, well, I think we've pretty much covered things. All Grey Matters, have you got anything that you would like to add to this?
Yeah, I was about to jump in and say I need to go, but I do have a question. Is it possible to share my screen with you?
Yes, sure. I'll just stop presenting mine. I just remember you can select just the app that you want to share rather than your whole screen if you wish.
I am working on it. Hang on. Okay.
Yep.
Okay.
This is the same capture I used from Stellarium on my video, and this question is mostly for Astronomy Live, because this will show a counterclockwise rotation. The way I have this set up is it's the viewing point is from Phoenix, Arizona, and it's on the same day and just before the time that Mr. Thrive is talking about. So I'm going to go ahead and speed this up. And as we come to the time that he's talking about, the moon is at the apex of its orbit right here, and it's just starting to come down. Do you see that counterclockwise rotation?
Yeah, yeah.
Is that unexpected? Because this is set up right now to simulate an equatorial mount.
No, that's libration at work. If you look at NASA even puts out videos usually once a year from LRO showing simulation of libration for the year, and you can see the moon wobbling around. Of course, they're very heavily accelerating it. You know, days go by in the span of a few frames instead of just hours. But yeah, no, that is normal given the polar alignment. Yeah, that's what the libration motion will look like. The funny thing is, a lot of these flat earthers and others will seize on the NASA video and say, okay, look, you know, they're showing here how much the moon should wobble. We're seeing a lot more than that, and we're seeing it faster. We're seeing it over the course of a single night, you know, rotating 180 degrees. That's not what this video shows. And they're right, because that's not what it shows. That these videos and this animation are showing libration, which doesn't affect the moon to the extent that field rotation does. Field rotation is a much larger effect. So you are, you know, when you're viewing the moon from a polar aligned perspective, you have to keep in mind that it's polar aligned. It's not aligned to the moon's orbit. It's aligned to the Earth's axis of rotation. And so the moon is not orbiting with 0 degrees inclination over the equator. It's orbiting with an inclined orbit. And you will see a change in the orientation from even the equatorial perspective. Even on the equatorial grid, it'll appear to rotate. And so one of the things I've done in my spreadsheet, for example, is calculate the position angle of the moon's limb to help compensate for that, and basically allow you to determine what the angle of the moon's limb should be relative to the local horizon. Now that breaks down when you have a full moon, because the moon's limb can be basically on the top or the bottom of the moon when you're very close to full moon. And so it doesn't really make sense intuitively, but it actually is correct. It's just it doesn't correspond to the moon's surface features. But just about any other phase, when it's gibbous or crescent, you can determine whether that crescent should be horizontal or vertical based on calculating two things: the amount of field rotation and the position, what we call the position angle, which you can calculate by knowing the moon and sun's right ascension and declination. And you can calculate that angle. And so you have to put those angles together to get the total apparent orientation of the moon. Field rotation alone won't get you there. It's a vital component, but it's not the only component. So that's why I've incorporated that into my spreadsheets as well. And that's what you're kind of seeing. There's the effect of that. If you were only looking at the field rotation angle, you would see the same wobble in the moon. And that's kind of what you're doing by looking at the moon in Stellarium or any other program from a polar line perspective and hyper accelerating it. And so, but even so, the amount, the rate at which and the amount at which it rotates is not as much as field rotation. However, I know that, you know, Mr. Thrive and Survive is going to say, well, I still saw rotation. I thought, you know, you said that a polar line perspective wouldn't have any. And no, the point is always that it doesn't have field rotation, but that's not the only rotation. That's not the only thing affecting its apparent orientation. Again, you know, like my two images here, you can see a little bit of change in the perspective of the moon. And maybe you could say that part of this is a bit of a rotation, but it's not much. It's certainly nothing like the altitude azimuth perspective.
I appreciate your thoughts on that. I think that's the point he's trying to make at this point, is that he doesn't understand where that counterclockwise rotation is coming from. But I do need to, I actually have a job tonight to go to, and I'm going to have to get out of here. And I appreciate the opportunity to be on the show with you.
Thank you for joining us. We appreciate you coming along, and hope to do it again soon.
Thank you, Dazza. I'll see you next time.
Have a good night.
Good to meet you. Good to meet you, Gray.
Nice to meet you too, sir.
Okay, now Astronomy Live, I think I will just double check with you, because I always defer. I mean, you're a much more skilled and experienced astronomer than I am. So I just want to check something with you regarding something I said earlier about the counter clockwise rotation that we saw. Let me just present my screen. Okay, now I've got that in equatorial mode. I'll just change that back to local. So we're discussing, let me zoom in on the moon again. We were discussing the counterclockwise rotation that we saw at the start. I'll run this forward in 1 minute increments again. Let me turn on the pole sticks and so on. Surface, there we go. That'll make it easier to see. So as we run this forward, this is on, let me change it to February 16th, 2019. As we run this forward, we see this counterclockwise rotation.
Mm-hmm.
Then it slows down, and then it starts heading back to the clockwise rotation, which is quite pronounced, especially as we're approaching the meridian.
Mm-hmm.
And then it's tilting right over. And then after a while, we see it starting to come back to the counterclockwise rotation. Now, my explanation that I've given for that, and I just want to double check on this, is that if we zoom right out and go to an all sky view, now I've got north at the bottom being an all sky view. We've got west on the left, east on the right, and there's the moon. Let me just bring that back a few minutes so it's right on the horizon. And I'm going to turn on the local path for the moon, and I'll step this forward by hours so we can see the path that the moon is taking as it crosses the sky. Now, when I was comparing the views and actually looking at when that that counterclockwise rotation actually slowed and stopped and became clockwise rotation, I noticed that the time coincided with when it was crossing the east-west line. So am I correct in my thinking that part of that rotation was because we were crossing over more than 180 degrees of the sky, bearing in mind that the moon was rising in the east-northeast, crossing over to the southern half of the sky before setting in the west-northwest? Am I correct in thinking that that is because we were crossing more than 180 degrees of sky, or have I got that wrong?
Yeah, that sounds right. That's one way of looking. I think that's a correct way of looking at it. The way I just tend to think of it is just imagining if you couldn't see the horizon, if you could see through the Earth, right? It would rotate counterclockwise at times, right?
Right.
And sort of make this, for lack of a better term, sine wave motion, where sometimes it's clockwise, sometimes it's counterclockwise. And so I think you're right in terms of the way you put that we're seeing more than 180 degrees of seeing it travel a path that's longer than 180 degrees. If you could see the full 360 degrees, which you can't because you can't see through the Earth, but if you could, it would appear to be rotating in a counterclockwise direction at times, and then clockwise at other times as it crosses the meridian. So yeah, it does make sense that's the reason for it, and that seems to be a valid way of putting it.
Right. Well, with Starry Night, of course, I do have the ability to hide the horizon.
Yes, exactly.
So, we'll do that, and I'll just turn on the horizon line. There it is. So there's the horizon line, if we could see the horizon. And we'll zoom in on the moon, and we'll just run this again and see what sort of rotation. So there's the counterclockwise rotation. It slows down. As I said, it was around about 6:30, I think. It seemed to stop, and then we started at 10:30 was transit of the meridian. There it goes. And there is the rotation clockwise, slowing down, and now it's starting to rock back the other way. Now, bear in mind that the horizon would be coming up about now to hide the moon from our view, but we've hidden the horizon so we can still see the moon, and here is the moon rocking back. So again, we've got this whole field rotation thing at play, haven't we?
Right. And so another way of looking at it, if you are hiding the horizon here, the meridian is no longer a line that ends at the horizon. You could actually theoretically draw a meridian that goes all the way around to the opposite side, right? So as it crosses the anti-meridian, it will be rotating counterclockwise. As it crosses your local meridian, it'll be traveling clockwise. I got to take off here, Dazza, but thanks for having me on.
Okay, well, thank you for joining me, and thank you to everybody who has joined for the broadcast, and we look forward to doing it again. Good night, everyone.